We start with a discussion on VSEPR theory, or in the lengthy terms, the valence shell electron pair repulsion theory. You must be wondering, what is this cartoon kind of a thing which I am showing on my screen? Well, to understand this theory, you have to really understand this cartoon. This cartoon is nothing but I'm showing you two negative charges. One is small, other is big. Now if I ask you, if there is a fight between the two, who will win? I'm sure you will respond very clearly. If this smaller guy is there and the bigger guy, naturally the bigger person will win. The bigger charge will win if this is the scenario. Now, this is the logic behind VSEPR theory. Let me explain now. Let us consider Nh3 molecule. You see, these are the bonds, and these bonds have the electrons. These electrons are shared between nitrogen and hydrogen. Similarly, there is a nitrogen hydrogen. This electron is shared between another nitrogen hydrogen. There is another one, this one. But the topmost electron is not shared with any hydrogen. It is exclusively with nitrogen atom. So in a NH3 molecule, say that there are three bonded pairs of electron. The bonded ones are the one which are with hydrogen. When the electron pair is between two atoms, it's called bonded pair, and when it is with only one atom, it's called lone pair. So this is a lone pair. Now see that this bond pair is with a positively charged nuclei. So the effective charge, the effective negative charge is less in these three cases, because nucleus of hydrogen has positive charge, therefore net negative charge becomes less, whereas this charge is very strong because it's without any other positive nuclei, like hydrogen in this case. So this negative charge therefore becomes something like this, and these charges here, negative, becomes something like this. So you will surely say that in situations like these, the lone pairs here will dominate. It's like this, the stronger person, lone pair, will dominate bond pairs. Lone pairs are sometimes referred as LP and bond pair as BP. This is basically for the same reason that the lone pair has more negative charge. So you will say that if we have situation where you have two lone pairs, so you will say that lone pair repulsion will be greater than lone pair bond pair, which will be greater than bond pair and bond pair. This is for the same reason that the charges here, the negative charges here, will be very large. In this case this will be large, but this will be small, and in this case both will be small, and this is the reason that this repulsion will be maximum. And this decides the shape of the molecule, because due to repulsion the atoms will try to move away from each other so that the energy is minimum. So moving away is important because energy gets minimum, and therefore molecule gets stabilized. Therefore in any atom you will say that there will be a repulsion in the valence shell electrons so that minimum energy configuration is achieved, and this is called VSEPR theory. Hello and welcome to this very important lecture where we'll try to understand how we predict shapes of molecules using VSEPR theory. We have already discussed that the basic concept is the repulsion of the bonding and non-bonding electrons, and this leads to the shape, and the shape is determined by number of bonding and non-bonding electrons in the molecule. So these are the critical things that you have to remember, and in order to determine the shape, the Lewis diagram must be drawn first, because this will give you very important clues about the shape. And then when determining the shape of a molecule with a multiple bonds, treat the multiple bond as if they were single bonds, that is one bonding pair. We start with the central atom surrounded by 4 bonding pairs, that is 4 atoms, for example. Now if we see this situation, the central atom is placed at the center of a sphere, then each of the 4 pairs of electrons will occupy a position to be as far as possible. This will result in the electron pairs being at the corners of a regular tetrahedron. Therefore these molecules are said to have a tetrahedral shape, and the angle between these will be 109.5 degrees. Let us see this with an example. We take an example of CCl4, and you have carbon at the center, and the 4 corners are occupied of the tetrahedron by Cl atoms. So this is a way of depicting this. This is another way of depicting 3-dimensional bond, and the angle between this is 109.5 degrees. So this tetrahedron is base for deciding shapes of many similar molecules. For example, NH3 has 3 H electrons like this, and there is a lone pair. Lone pair will not be considered in the shape. So this goes out, and the shape thus obtained for NH3 is called Trigonal Pyramidal. Now this can be easily understood. For example, in NH3, if this is the lone pair, this will go off, and you will get a shape which will be somewhat like this, which is the Trigonal Pyramidal. Now due to the increased repulsion, the repulsion is high by lone pair bond pair, which we discussed earlier. This repulsion is high, therefore the angle contracts between H and H and is almost around 107 degrees. Whereas interestingly, in the case of water molecule, you have 2 lone pairs, and these are shown by this here. So these 2 lone pairs are not taken into consideration, and 2 goes off, these 2 lone pairs. So in this tetrahedron we will hide 2 lone pairs. For example, we hide this, and let's say we hide this also. For simplicity, we are doing this. So the shape of water molecule therefore is bent, and we see something more significant here. There are 2 lone pairs compared to NH3. The repulsion is even more. This repulsion is very high, and this angle further contracts. The HOH angle is simply around 104.5 degrees. To further clarify, this is NH3. This is summary of what we discussed just now, which means that simply the 4 pairs of electrons will be arranged tetrahedrally in situation where you have 2 bonding pairs and 2 non-bonding pairs, and the result is a V-shaped molecule, and the angle is 104.5. The angle decreases by 2.5 degree compared to NH3 because of high repulsion. This is water molecule where this is exhibited. Now we discuss molecules with central atoms surrounded by 5 pairs of bonding pairs. You have 5. Earlier we had 4. Now as with tetrahedral molecule, the electron pairs will arrange themselves as far as possible so that repulsion is minimum, energy is most stable. And to achieve the maximum stability configuration, the atoms arrange themselves in triangular bipyramidal shape. This is something which you have to remember, which consists of two pyramids. You will see very soon now, sharing the same base. Now in this type of molecule, the three atoms making the base will lie in the same plane with the central atom in the middle of it. The other atoms will be positioned above and below this plane. Soon it will be very clear to you. The bond angles with the base will be 120 degree and the bond angle with other atoms and the base will be 90 degree. Let us see this little more in detail. So example for this is PF5, and if you see the three-dimensional structure, the triangular base is this. These three atoms. The top is this, which is perpendicular to this triangular base, and the bottom is this, which is again perpendicular to this triangular base. This triangular base is shown here in this diagram like this. See, this F is included, so I'll just include this F. This is a triangular base. Now the top atom is this, bottom is this, and PF5 shape is shown like this. So the angle here in the triangular base is 120 degrees. This angle is 120 degree, and angle between this and the top or the bottom is 90 degree. This is shown here in this more clearly. PF5 obviously had 5 bonded pairs, 1, 2, 3, 4, 5. But suppose one becomes lone pair, then in that case you won't consider this in your scheme and you get a new kind of a molecule. Let me explain now. These are the molecules surrounded by 4 bonding pairs in one lone pair, and they look like this, and they have become like this just because of this effect. This is called a seesaw shaped molecule. Why seesaw? Because this molecule, if you turn like this, it looks like a seesaw here. One example is SF4, and this shape is called, as I said, seesaw. Now I'll discuss molecules surrounded by 3 bonding pairs and 2 lone pairs. So what will happen is one pair will go off in the shape, we will not consider this, and then other pair will also go off. Let's say we take this, and the molecule will look like this. This shape is referred as T-shaped. So this is T-shaped molecule, and this happened when 2 become lone pairs in 5 pairs of electrons. And the example is ClF3. Now we discuss molecules with central atoms surrounded by 6 pairs of bonding pairs. This from 4 to 5, now it's 6 pairs. Now in order for 6 pairs of electrons to be as far as possible so that energy is minimum, they have to be a regular octagon. In this situation, the central atom is at the center of square plane made of 4 atoms, and other 2 atoms will be placed above and below the plane. So you'll have a square plane and 2 atoms will be above and below, and in square plane you'll have 4 atoms. All bond angles are 90 degree. The example is SF6. These are 4, these 1, 2, 3, 4, they are square plane atoms, and on the top this is perpendicular to the square plane, and the bottom you have 2 atoms. So if I see in this is the square plane for simplicity, and these are 2 top and bottom atoms shown here also for clarity. And you can see this thing also, all the angles are 90 degree, and this is the model that you have for these kind of atoms. Now obviously you will immediately guess now if one of the atom instead of one of the atom you have one lone pair, this will go off and you will have a new kind of molecule. So this is what we'll discuss now. But before I go on to this, you must remember that the shape is called octahedral. Octa means you have a shape which is similar to octahedral. Now what happens when one becomes, out of 6 pairs, one becomes lone pair, and when one becomes lone pair, this will not be considered and you will have this kind of a shape. This shape is called square pyramid. Because this is square and this is kind of a pyramid, and the example for this is BF5. Extension of this concept is, out of 6 if 2 become lone pair. Let's say this XCF4, you have 2 lone pairs here, this one and the below one. So when this happens, this will go off. The top one is a lone pair and the bottom is a lone pair, and you will have this kind of a molecule. This molecule is, example is XCF4, and this is called square planar. You should also consider some molecules with incomplete octet, how we predict for them. For example, molecules only which have 2 bonding pairs on the central atom will have linear shape with a bond angle of 180 degree, and with 3 bonding you will have a trigonal planar shape. For example, BEF2 doesn't obey octet rule and it has 2 bonding pairs. They are separated maximum by 180 degree. This is the Lewis structure and the bond angle is here 180 degree. In BF3 though, there are 6 electrons, 3 pairs, and they are on 120 degrees to each other in a plane. So planar at 120 degrees is the answer for these kind of molecules. So you have to remember that in order to predict the shape of a molecule, you must draw the Lewis diagram for the molecule and then determine the number of bonding and non-bonding electron pairs and compare this with the chart, the kind of thing that I have discussed till now for general shapes, and you have to memorize these general shapes. This chapter is very important, and in this the concept of VSEPR is of utmost importance. Therefore I would like to play a movie for you so that you get the complete visualization of these molecules. So one by one molecules will come. This is a kind of a linear molecule, 2 bonded pairs. And you should imagine this one is like BF3, trigonal planar, 3 bonded pairs, 0 lone pairs. Recall we discussed in the lecture about BF3. Now if one becomes lone pair, it will become bent molecule. And you should compare this with the molecule that you are studying. Again, this is bent, 2 bonded pairs and 2 lone pairs. We have studied this as well. One molecule in the lecture, try to recall that, which was this molecule with 2 lone pairs and 2 bonded pairs, and we said it's a bent structure. This is Trigonal Pyramidal with 1 lone pair at the top and 3 bonded pairs at the bottom. Try to recall which molecule this was. We discussed this also in the lecture. You have a T-shaped molecule. Can you recall this? What was this which we discussed? 3 bonded pairs and 2 lone pairs. This is tetrahedral, 4 bonded pairs, no lone pairs. Very common basis of organic chemistry. CH4, I am giving you this now, or NH4 for instance. This is a seesaw, 4 bonded pairs and 1 lone pair. Try to remember this. We have discussed this molecule as well. Seesaw. This is square planar, 4 bonded pairs and 2 lone pairs. XCF4, just to remind you. So some of the molecules I am giving you, some of those you have to recall. Well, this is Trigonal Bipyramid, 5 bonded pairs, 0 lone pairs. And now if you make one of these lone pairs, it will become square pyramid, 5 bonded pairs and 1 lone pair. This mental picture is very important along with you memorizing the thing. Now it is octahedral, 6 bonded pairs, no lone pairs.